Okay, we are starting the afternoon session, discussion session for anybody who's following us, still following us on YouTube. We can turn on the light, maybe. No, it's tablet ready. There is everything ready. But I should check. We're a little bit late. Check. All the things are where they're supposed to be. Content question. Right. So sometimes you remember, sometimes it doesn't. Okay, so what do we want to discuss next? Right. Yes.
My wireless is in. Either do something relative, or do something relatively contained.
You guys have any
Start.
Sorry? Any preference for what to discuss next?
So the stars have already been discussed.
Yes. I can reorder if that's helpful to put everything together that we've already discussed. Yes.
Symmetries from a difference we already discussed as well.
That's true.
So for me, I'd like to have more clear in my head. What is the difference between the indifference and the fact that I don't know, because those two are two different things, and how what you were saying relate to the codes that he was talking about, because I don't have that in my head.
You could try a bit to have that explain briefly.
So let me, okay, so let's share again
There's a paper that I wrote like maybe 20 years ago already. It's called Evidence of Symmetry versus Symmetry of Evidence.
Okay.
Because there's a difference between the two. So symmetry of evidence means that the evidence that you have is symmetrical. And that is the case, for instance, when you're completely ignorant, because you know nothing is completely symmetrical. So that is symmetry of evidence. And that is represented if you have a set of probabilities by the fact that this is closed under the permutations. That is the one that you want. So you have a symmetry of evidence. Evidence of symmetry is much stronger because then you have evidence that there are symmetries around.
Right.
Right. You cannot distinguish between these two if you have a single problem.
Then I understand. How does it relate to the eye, to the indifference?
The indifference describes evidence of symmetry because you are saying you're accepting an option and you're accepting you're accepting the difference between the two. So you're saying these are actually the same thing. So you're stating that they're the same thing, and you can only do that if you have evidence of symmetry. Okay. If you believe that there is symmetry.
And how do I talk the other one in the AD context?
In that case, you would. Oh, you could do it. Can I just write it on the so there's the two conditions.
Give me the tablet so that I also have a record of it, which you know. Yes. Here. And this would be screen specific app. There you go.
Yeah. Do it this way. So let's first begin with symmetry of evidence. There's many ways to do that, but for instance, suppose that your symmetries are using a monoid, right? So T would be a monoid of symmetries. I'm going to look at the case of gambles, or I could do options. Yeah, so I have options U, and then T of U, where T is an element of T. This is the transformed option. If you have symmetry of evidence, so there are like 3 types of models that you could use to express this, and I've tried to go through all of them in my talk. The first is the AD models, accept desirability models. The second is the lower and upper provisions. Okay. And the third one is the sets of precise provisions. So these are more or less equivalent models, right? So in terms of let's say, I'll write down all 3 of them. So the one says that T of any set of acceptable gambles should be included in the acceptable gambles, and T of the rejected gambles should be included in the rejected gambles. So T is the direct image. So I take every element of A, right? So this is the weak. This is a symmetry of evidence. This is weak, right? In terms of sets of probabilities, it says that if P is in my set of probability, then the transformed P, so P after T, if you want, is also have to be in. So this is the symmetry that you were talking about. In terms of upper probabilities or upper provisions, it's a bit like P is equal to P after T.
So you make the transformation and
So the upper expectation is invariant. That's the thing. Now, of course, if I have if my set of probabilities is a singleton,
right,
then these two coincide.
Yes.
Right?
Yeah.
So that means that with precise probabilities, I cannot distinguish between symmetry of evidence and evidence of symmetry. And that's why the principle of indifference or Laplace's principle of indifference, when you apply it to precise probabilities, gives you the wrong answer because you can't use these models to distinguish between the two things. So that is why. Okay, so now let's go to evidence of symmetry.
Great.
So in the case of evidence of symmetry, I already explained this. So you have a set of indifferent options, which is the linear span of the TU minus the SU, right? And then you should have that A is A plus I, and that R is rejects R plus I. That is the formulation in terms of the accept reject models or accept desirability models. Here, what you have is that
It'll be the same.
P is P after T for all P and M.
Yeah,
Yeah.
It's just the same thing when you move it.
Yeah, and here, so it must be applied to the sets. And here what you have is that the difference between U minus TU must be greater than 0. And in fact, equal to 0. That follows from that. Or, yeah, and you could use SU minus TU, doesn't it? So that is, but because these models are not additive, it's not the same. So you need to look at the differences between the two, and that is those are the three things, right? That is what happens, right? And of course these are in a sense all equivalent to each other per row, but sorry, the columns are equivalent, but the rows are different. So the weakest model is the top,
yep,
and then the strong one is the.
No, I understand. Okay,
Is that clear now?
This is a very good characterization. Yeah, that's good. It's nice and precise. Yeah, that makes sense. And now for yeah, one under the how does this translate to cones? How did the A?
So the left one is the cones. The left thing is the cones, and the middle one is the probabilities that are the dual cones, in a way.
Okay, so can we have an example like of a heads or tail of the symmetry of evidence with the cones, so that I can
symmetry, yeah, for heads and tails, symmetry of evidence could be well. Yeah. So let me do the symmetry of evidence. So with a cone, I have something that is symmetrical, a symmetrical cone around the first. So
what am I plotting here? This
is heads, this is tails.
Yep.
These are the gambles. The points are the gambles. And so I have this set here. This is the boundary of the cone of acceptable gambles. Right, so you see this? It's a cone of acceptable gambles. Everything that is on the right-hand side of these two lines is acceptable, right? And it's symmetrical with respect to the first diagonal.
And the first diagonal,
and that respects
so the gambles where
those are constant.
Equal man. Okay. Oh, yeah, it's a constant.
Those are constant gambles, but it's symmetrical in the sense that if I accept a gamble on heads and tails, if I permute the two, they will still be accepted. So these are the weakly symmetrical gambles.
Yeah.
Symmetrical gambles, or in the strongly symmetrical will be, there's only one in this case, I think, strongly symmetrical. Yeah, and that is this one, right? So now it's a semi-plane, it's a precise probability. There's only one precise probability that is symmetrical in this case with respect to the permutations, and that is this one where we have a semi space. So in this simple case, there's only one precise probability model. So there's only one model that respects the symmetry. So,
and it's still a set of gambles because whenever I have one value that is greater than the other or the negation of the other, I'm gonna win something.
Yeah. So it's a semi-plane. The probability is determined by the normal to the semi-plane, and this is so the dual cone in this case is a single
line.
It's a single line, okay.
Yeah, whereas the dual cone here, in this case, would be, so the orthogonal to this and the orthogonal to this would be something like this. This would be the dual.
Okay, so that will represent an uncertainty in probability.
Yeah. But the dual cone is also going to be symmetrical, of course, with respect to the symmetries.
Right, so the dual cone with the probability, I should then think that there is a line, 45-degree line between T and H that represents the unit, and that's okay. So when I have some uncertainty on the probability, then my other cone sort of closes up a little bit. And when I have complete uncertainty, then I just have the upper.
Yeah,
right one.
and that is also symmetrical, of course, right?
Right.
So the complete uncertainty is this one here.
Yeah.
Right. This one, and it's also symmetrical, as it should, because it's the smallest one that is symmetrical.
Okay. And so when I'm representing the gamble, each point is a different gamble, and then they form a cone, because if I accept a gamble, anything rescaled positively, I get it, okay? Okay, now if I finally can start see it, because I could kind of see it before, but now I really don't.
So it's the only self-dual one, the vectors is the only self-dual one that is symmetrical. Yeah.
Okay, so if I have like a more complicated space, so if I have like 3 points, this sort of generalizes very well, because it would just be again the positive grant. How do you call it?
Octane?
The orthos,
Okay. And then you basically have the same thing.
Yes.
Opens up and
Yeah.
close, okay.
Yeah.
And then if I have something like block sphere or whatever everything, so again, I would have a cone for which the unit intersection would be my block ball, because it would be the whole ball, because it's all the probabilities. And then the set of gambles is going to be some other dual cone.
Yeah. And it's harder to draw, but you can do the same thing for measurements, but it's a bit harder to draw because you need 4 dimensions to make it interesting, right? Because the set of measurements for a 2-dimensional space is 4-dimensional, right? It's n square. So the small for a qubit, the set of measurements is 4.
No, no. I was thinking for like classical
For
mechanics.
quantum. No, just for quantum.
Yeah, for quantum, yeah.
For quantum, yeah, it's a bit more difficult to draw, and
Well, but even there, it's the set of measurements that you can make is infinite dimensional, because I can pick any direction.
yeah, it's a linear space, right? Yeah, but what do you mean infinite? So I have a 4-dimensional set of space of measurements, right? For a qubit,
It's 4-dimensional.
it's spanned by the 4 Pauli matrices.
Once you have it as a qubit, you've already picked an axis, right? You've already picked your 2-state system.
No, not really, because I can, okay, so. Because they happen to be linear combination of each other.
Yeah.
Well, if I have, if I'm actually, instead of making a measurement on a direction on a sphere, like a classical sphere, then that's infinite dimensional, because every single direction is going to be a different thing. Okay.
But it's harder to draw, and the actually the vacuous set will be the block sphere if you reduce it to 3 dimensions. If you represent it, if you disregard the unit direction, the I direction, and only take the sigma x, sigma y, and sigma z, then it will this smallest cone will be the block sphere of radius 1. That will be the.
Okay, I'm satisfied.
Good.
Actually, if you're interested with an example in our paper, there is an example with the block sphere, and we started with the position of the 2x2 in the polymet.
Yeah.
And you have the coordinate b, x, y, and z. Since we wanted the gamble on the positive code to be positive, you get this code.
Yeah.
And then so we started with this corresponding score, and then you can take projection in one of those those variable to see how it looks like, that is
Right.
nice. And then when you compute the dual, you get so this is the probability case, and the dual here is the block sphere.
Yeah.
And then we do it a probability or equivalent of probability and dual inside.
Okay. Next topic.
Right. So we're coming to the more difficult issues, I think. The relation between continuous embedding of a topological vector space, in a topological convex space and a topological vector space, and the relation to the cancellative property.
Yeah, let's do the
And the
cancellative
Activity of the
property.
topological space, those are all related to each other, right?
Yeah, but the cancellative property is a lot easier.
So going through the necessary and specific conditions to define ordered quantities.
Actually, I think it's easier if I share the book because those things are going to be easier. So
Also, I have a question, please. Why do you think it's not the cancellative probably is not natural or
Yeah.
well, why can you not assume it? It seems to me very natural, no?
you have to justify it. Like you have to make a coherent argument. Let me show you how the other.
Okay, yeah, the other ones, yeah, would be clear, yeah.
And then you say, oh yeah, I can see an argument like that because I don't see it. I really don't see it. So, okay, so
You get to hear that a lot. It's always like, oh, well, that sounds very plausible. But never have to say like, look, I don't want accept just anything that's plausible. I want to know that it's definitely necessary in any physical theory.
Yeah, that's.
Because I might say like exclude real physics without knowing it.
So
Our base theory should be relevant for any physical theory that may be developed in the indefinite future, right? So we really want things that are.
So this is the axiom of mixture, right? It says the statistical mixture of two ensemble is an ensemble. And formally, an ensemble space is equipped with an operation plus that takes a number from 0 to 1, two ensembles, and gives you back another ensemble called mixing, noted with the infixed notation with the following property. So it's continuous. So why should we say that it's continuous? Justification. The axiom captures the ability to create a mixture merely by selecting between the output of two different processes. Let E1 and E2 be two ensembles represent the output of two different processes P1 and P2. Let a selector SP be a process that outputs two symbols, the first with probability P and the second with probability P bar. Then we can create another process P that, depending on the selector, outputs either the output of P1 or P2. All possible preparation of such a position will form an ensemble. Therefore, we are justified in equipping an ensemble space with a mixing operation that takes a real number from 0 to 1 and two ensembles. Okay, got you two preparation and something that can select one from it.
Yeah, so you're going to use probabilities, random selection to actually justify mixing.
I think so. That's the
That's the
simplest
idea.
way.
That's-
So
That's why I
What-
was saying and justifying that it's a number between 0 and 1, it's the same justification as for probabilities.
Right.
That's the idea of convexification, right? That is typically also used in decision making. If I don't have enough options, I will convexify them by flipping a coin to make sure that I get, that I can, in fact, that I can use the what is it, the interior point theorem, that is the reason why you do it in game theory.
Okay.
Yeah.
So-
And even, sorry, without a selector, you can just combine data afterwards. If you have two experiments, you can take like run this 5 times and run this 10 times. If you combine the data, you have like a combination 1/3, 2/3.
Right. So
It's
this is
another
not
way.
the only way to do it. So my favorite example that I have in my head right now, I have to put it somewhere. Do you know those things that you have nails in a triangle shape? And then you put a ping pong ball and then it flips around, completely randomize it. Okay. So imagine that you have two outputs and you have like something that you can move where the middle point is. you're effectively changing the probability, changing the mixture, but that P is no longer flipping a coin. It's a physical thing that you're moving. So the fact that here I'm using P as a probability doesn't mean that that has to be a probability. It can be whatever other, but at least I can do this.
You can do this.
Therefore, I need to be able to do it.
Okay, yeah.
Okay, so that's the first thing. So given that mixing represents an experimental relationship and all experimental relationship must be continuous in the natural topology, which is results that I have there, mixing must be continuous functional. In general, mixing coefficient P corresponds to a value from a continuously ordered quantity between 0 and 1, as defined in the previous chapter, and therefore the natural topology is the one of the reals, and this justifies continuity. Okay. So I'm not only telling you that the parameter is the real because it's the only one that it can be, but I'm also telling you that that's the only topology that I can put there. So I know what these things are.
The crucial argument is that experimental relationships must be continuous. That is
In the natural topology, yeah. So this is like the whole chapter before this this one here, verifiable states in an experimental domain. And it basically tells you that your physical theory has to be generated by experimental verifiable statement. So any statement in the theory must be a basically the closure of a set of countably many verifiable statement closed under negation, countable disjunction, and countable conjunction. Because those that's the algebra for which you can close tests. Because you can create a loop, right? And the loop are going to go through countably many things, and it can check whether if one terminates successfully, then I exit the loops and I'm successful, and that's the or I can check the loop. If one is unsuccessful, I get out. That's the end. Mm-hmm. And the negation is just I run it. If it terminates and is successful, I return unsuccessful, and so on. So that's really the sigma algebra represents that algebra, and the open sets of the topology represents the verifiable statements, the one that terminates successfully infinite time, if and only if the statement is true. And because when you have a relationship, you can make induction. Like if you have A that causes B, then a verifiable statement on B is indirectly a verifiable statement on A. So if the water temperature is a particular value and I measure the water density, since the water density is a function of the water temperature, I can go and say, since the water density is within these values, then the temperature must be in this value. And so that's done in a completely precise way. So I can really, that has to be true. Like there's no.
But it seems to me here that in order to satisfy your axioms, what you're saying is, I know at least of one way in which I can satisfy them, and that is by using probabilities.
It depends.
For instance, for
the existence of the mixture, I only need to say there is at least one way to do it. Therefore, the function must exist.
But for instance, for the associativity, you use the argument of probabilities.
Yes.
There, but that seems to me that you don't prove it for everything. You prove it just for the probabilities, right? Well, the argument is based on the fact that it works for probabilities.
Yes.
But
you say if I use P as something else, what guarantees me that it has to guarantee me? Interesting point.
Yeah. A lot of people use complex number. Why not?
The order is still on.
So in that respect,
so that there would be a different function, right? So if I had a complex number, I'm not saying that it doesn't exist, that there would be a different thing. So what I'm saying is that at least I can do it with this, and this gives me something. And then everything that follows this one that I know must exist must obey the same rule, otherwise it's not the same function.
Yeah. Okay, but if you do it this way, you would have to make this argument more explicit than
you're right.
Yeah.
Sorry, for justifying it, we could make the justification.
Yeah, this looks like justification by example. Whereas,
Well, it's not really by example, it's I'm giving you what is it that the axiom is representing.
Yeah,
So that
yeah.
every time that you have a proof and you have something, you can say, oh, this is what I'm representing,
what I was looking for.
right? And you're right, there is a sense in which this can represent multiple things, and I'm not showing how it is representing multiple things that are equivalent. But it is also true that you can always say, if there is something else that you're doing some type of mixing, that it's not this,
That is not like this.
that is not statistical mixing, it's gonna be something else.
Yeah. Yeah.
So I can make that explicit, like that anything else that follow these rules is called statistical mixing, not just this flipping of the coin.
Yeah.
If if it obeys the same
Okay.
property.
So
And then since it's indistinguishable, then I can use the flipping of a coin argument to justify all this. Okay, so the point is that now I have to justify all these things. And that's what you do. If P is 1, the output of P will always be the output of P1. This justifies the identity property and so on. And so if P and P1 are the same process, so then the output of P will always be the output of P1. This justifies idempotence. The order in which the processes are given does not matter as long as the same probability is matched to the same process. The process P is identical under permutation of P1 and P2. This justifies commutativity. And if we're mixing three processes, P1 and P2 and P3, as long as the final properties are the same, it does not matter if we mix P1 and P2 first or P2 or P3.
Yeah.
And now the mixing, the consecutive process property would be that thing that if I mixed A and B and A and C and they're the same thing, then B and C are the same. I don't see how to do it.
So the way it is used in preference modeling is that you have an X and a Y, or an A and a B.
Yeah.
And one is preferred to the other, if and only if, for any third, if I mix the first one with the third and the second one with the third,
Yeah.
the ordering is going to be preserved.
Yeah.
If and only if. And it's that one that makes sure that you can embed it, that you can embed this ordering, which is only based on the cone, into a linear space. That makes it sure that you can do that.
Yeah. This is the thing that Definetti had, and that I also try to retool for something else. And in this case, okay, so you would be saying, yeah, but I don't have an ordering right here. Okay, the entropy is kind of like giving me the ordering, but here I don't have a.
Well, I think if you have, I don't know. So yeah, I'm not saying, but even that is not justified, right? I mean, this is something that is an axiom, or kind of a rationality axiom that they impose, but.
Yeah, you would say no, yeah.
Yeah. I mean, I think that these people introduced it because it was convenient and it helped them prove their. I mean, I think the way they do it, I think, is that, okay, I want the representation by probabilities. Well, if it is represented by probabilities, it must satisfy this because probabilities satisfy it. So this is what I'm going to need. Right, that's how they did it.
Yeah, the reverse engineering proof.
Yeah,
what
right.
they needed, and then they just used.
So, and that's good for me for reverse physics when I want to understand the equivalence. But here, no, I can only prove what I can justify and say, no, this must be the case. So in case that I'm doing statistical mixing, the point is that I can kind of say I can put things together, and that's fine. But if I have two things and they're coming from other. Like, how can I make, because I have an equivalence, it's like I have these four things and I'm mixing them. I know that these two are the same, the coefficients are the same, and I know that the final thing are the same, and I'm saying that these things are the same.
Yeah, because you are mixing with the same coefficient with respect to any other P, no? And
right, but the point is that you're assuming that the mixture operator does not like hide the information from you. Because you're saying I can go back, and what does it tell me that has to be the case?
And how does because it's interesting that the entropy forces this, right?
Yeah, and I can show you how.
Because that is really cool.
Yes, that is really cool. So here's the consecutive property. And then there is the theorem, then ensemble spaces are consecutive. So then you have A, B, and E, and PA plus P bar E is the same as the other. Okay, so this is how it goes. It's a little bit involved, but here is how it works. So first, you want to show that if this is true for 1p, it's true for all the elements from 0 to p0, to that p0 that you have, right? And the way that you do it, you can essentially rewrite this PA plus P bar E as a mixture with the P0 plus something else that is still E.
Mhm.
And then you say, okay, but this part here is equal with a B. And then you re-put this together and you just switch the B at the end.
Mhm.
Okay, so this is true for whatever, everything. And now you want to show it for all the elements from 0 to 1. And this is kind of where we have to do it the opposite. So if you have PA plus this everything, so you want to find a P such that you can double the A and let the everything. And so you can find this magic P, and it's going to be this P0 divided 1 point P0.
And then will have it for rationals.
Huh?
You will have it for all rationals and then use the
Well,
continuity.
you have it for these, and then you say, but for any of these, I have it less, and for any of these, I have it less, and so on, and then you
You
can
get
cover
it for
them.
all rationals in a way, yeah? And then continuity?
Well, no, it's the thing before. So if you know that it exists for some,
sure, yeah.
it exists for before. So you just need to keep going further and further
Until.
and get everything else. So at some point,
Yeah, you just need to go to the right.
Yeah.
Yeah,
Just keep
not
going.
because you have the left already. Yeah, cool.
right? And so at that point, you do that, and again, you do it, with iteration. Now you know that it's all from 0 to 1.
Yeah.
And now you want to show that if this is true for all the 0 to 1, then it's also true that you can mix the A and B's with some other coefficient, and you're still good.
Mhm.
And for that, it's again one of these switcheroos. So you have this, and then you take these p lambdas, you put them on either side, and then you can switch the b from one side to a, and then you have the a. But then if it's true for a, it's also true for b, and so you're good. So you're basically saying that not only a and b are the same, but every convex combination of a and b have to be the same. And then now you use finally the continuity of the entropy. Basically, you want to show that the entropy of any convex combination of A and B is the entropy of A, and it's equal to the entropy of B. And then since the entropy when you mix can only be the same when you have when the entropy remains the same, then those two things have to be the same.
So this is the one direction, right? One implication. If there is a P that does this, then
Those things are the same.
that's true. And the other way?
But that's just
Trivial.
yeah, it's just trivial. There is no, like, you only have to prove it on the other side. Yeah, the reverse side is always true. So if A and B are equal, then of course this is satisfied.
No, what I meant, so in an ensemble space, so sorry, can I see the formulation?
So this one, or this one.
And where are you using that you have an ensemble space? So by an ensemble space means it has a what, an entropy, or where do
Right
you use
now it has a topology, it has mixing, and it has an entropy.
it has entropy. And where have you used the fact that it has entropy?
It's the last step. There you go. So before, what you show, just using the convexity, is that if this relationship is true for some p,
Yeah.
right, it's true for all the p's and for all the linear combinations of A and B.
Yeah.
Then with the entropy, you can show that the entropy of the mixture of A and B is equal to the entropy of A, and it's equal to the entropy of B.
So what you have is that if there is one P for which this holds, P0 for which this holds,
yeah,
you prove that the entropy must be constant on
the whole mixture.
And that's your statement. Is that the statement that you wanted to prove? I'm because I have trouble remembering
Right.
what
So
it was.
once you know that the entropy of a mixture of A and B is the same as the entropy of A and B, then you know. I don't know whether is this to do review. Review the next one. By strict concavity, this is true if and only if A and B are the same. Because
You use the entropy to prove the strict concavity of the entropy to prove that
Yes.
they must be the same.
Yeah.
Because you don't have that yet. Okay. Cool. That is cool.
right, so the continuity of the entropy shows that these have to be the same.
Yeah.
And basically, you go make these limits. You substitute the p's. Then you take these limits for where the II is goes to 1. So this goes to 0, and you get these. So the continuity of the entropy give you this, and then the strict concavity of the entropy proves that they must be the same.
That's a cool proof.
Can you go back where you take the limit? Say
Yes.
the limit of P, okay, of the mixture there is, or you take the limit because you want that element. So that's why you P.
Yeah, you're basically using the upper bound and the lower bound
Mm-hmm.
to sandwich in.
Okay, yeah.
Yeah, the lower bound is just the sum of the two, and the upper bound is the lower bound is because of
The strict concavity
concavity, and the lower bound is because your definition of the I
of the upper bound on the entropy. Yes.
for which you've already proved that it is 0.
Yeah, that's yes.
That's already proved, right? So that it goes
So
to 0.
what we're basically doing here is that since this is continuous, right?
Yeah. So your I goes to 0, and therefore you squeeze between the two.
Squeeze between the two. And so this is the magic, because again, when I started these axioms, I thought that the non-constellative part may be something interesting. And then I recognized that, with the entropy, actually, I was able to sandwich it in.
Okay, so if you have a concave continuous function on that set, it works. That's the idea, right? There's some strictly concave.
Strictly, but you also need a bound from above, because I need to switch. I need to sandwich them in.
Yeah.
Otherwise, you're not going to be able to force them in. Yeah, anyone will do.
Anyone that goes to 0.
Yeah, any like strictly concave function that also has an upper bound.
An upper bound
that sort of recovers that, then
forces this condition. Constellative property.
Yeah. And it's funny because at the end of the day, this is an optimization problem, right? You have instead of a concave, instead of convex, you have a concave, right? And it's it's again the existence of the maximum of the entropy, right? It's because you have that, and the uniqueness of the maximum of the entropy is because it's strictly concave, right? So it's basically the fact that you can make this optimization problem unique. That means that when you're doing it, we have two things that then it forces them to be the same.
This is really interesting.
Yeah, it was completely unexpected from me. Like it's as I said, it came as a.
You had a celebration that evening.
I didn't remember when.
I would.
There's so many like little things like that came out, because as I said, like it's kind of from my computer science and software engineering background. One of the one of the things it's counterintuitive is when you have few starting points, it's sometimes easier to prove a conclusion because you don't have very many things to work with.
Yeah.
So if you can prove the conclusion, it must be.
Yeah.
And you know that you have good starting points when you have very few things and you can prove a lot of things. And this is exactly why I'm like super stoked with this.
Yeah, you know that you have a good theory if you can do immensely many things using almost no.
Yeah.
That's what probability is for you, right? Like 3 or 4 axiom and
Yes, seriously. But even set theory, like, you basically have just one property, X is in Y,
Yeah.
and then you construct
everything.
It's kind of amazing.
The derivation of our recover ordered quantities. Oh, no, I think we're done. Are we done with the cancelative property? I think.
Yeah, there was some other interesting thing that, so since we are talking about the entropy.
Oh, yeah, we had the relation to the Renier entropy. There's another entropy related thing on the list.
That's the thing, but like I think, trying to think that there are other results like this that they might find interesting. So the vector space embedding, like once you have the conservative property, you can.
Yeah, then it's
Like the complication is that I'm trying to do it like in a way that it's a little bit more physical than just saying, oh yes, I do the span of one thing but the other. So that's kind of the way it's.
So but you're doing essentially the same thing. The span of V minus V.
It's not exactly that. So like what I do, I try to basically create differences.
Oh yeah, all right, okay. Yeah, this is another way of doing it. Yeah.
So,
And it doesn't depend on the alpha, right? In a way.
well, so I basically do this thing where I want to get a sense that the whole vector space, it's like a continuous zooming in inside the ensemble space. The problem of doing that, that I know right now it's a problem, is that I did a point where I'm zooming in, and that point must be in the algebraic interior. And there are cases in the infinite dimension where I might not have points in the algebraic interior, but I don't know if are physically significant. So for now, but so right now I need a point A in the algebraic interior, and then what I basically define are these abstract objects that intuitively, there you go. This is the idea. You pick A. And A is your like reference, which is going to be your origin, right? And then if you want to say, you see that A is 1/2 B plus 1/2 C, you're basically saying that the difference between C and A is equal to minus the difference between B and A. And if you know that D is a convex combination of A and B, and it's on the same line, what you're basically saying that is 1 D minus A is equal to 2/3 B minus A. And the same thing then for addition. If I have an F, and this F is 1/2 B plus 1/2 E, then what you're saying is that 1 minus F, so this one, is essentially twice B minus A and E minus A. So this is essentially the parallelogram law. So I have this intuitive idea for which you basically take these things that are defined as convex combination, and you define them in this essentially vector space. So what you need to show now is that you can construct a vector space out of these things. And that's the pain in the butt. And so I have these, differences which are a real number and two ensembles. And then you basically say that R B minus A is equivalent to S C minus A if there exists a K such that these convex combinations are the same.
This is like the cancellation property that you're using in a sense, right? Yeah.
Yes, like the cancellation property allows you to say this, and this is basically that these two things are on the same line.
Yeah.
And the difficulty here is that I need to define this equivalent class so that it works for all numbers. And if you do like the trivial things, then there's gonna be a zero in the middle, and the zero in the middle is gonna not make the equivalence class work in some respect. So what you use is basically you use this free parameter. There exists a k, so you avoid the zero because if it were zero, you just put a different k.
And then you have an equivalence class of such couples.
Yeah.
With real numbers, and that equivalence class exists precisely because of the cancellation property.
Exactly, yeah, exactly. And so then you have to prove that all these things have the right things and so on. But then you have a sort of a concrete way of thinking of the vector space that you're constructing.
The other thing about this, I think, is it's a bit of confusion with the plus and the constant compared to the definition of the mixture, no? Because somehow you are redefining them here, no?
Yes.
So yeah.
Because now what happens?
So this is the plus in the linear space, no?
Yeah.
Yeah.
So this plus here is in the convex space.
That is okay, yeah.
Because this is a condition, this is a mixture.
No.
And this mixture is with three things that are gonna sum to one, and these are plus s plus k, they sum to one. So these are still a relationship in the convex space. Then what you do later is that you define an addition on the equivalence class of differences.
Yeah.
And now this plus is an addition in the vector
space,
space. And therefore you have to go and check that everything works. And then it does, and you're happy and so on. There might be a more elegant way to do it, but this one works. And then you basically show that for every internal point, you can create a vector space, and then you have a natural embedding between the ensemble space inside. And here's the problem. It's a vector space in vectoring. It's not, I don't know that it's continuous. Because it's only done with the algebraic. I do not know the continuity.
But it's okay in finite dimension.
In the finite dimension, we have now a half-proven conjecture, thanks to the help of artificial intelligence, because I said, go figure out some stuff, and we should be able to prove it. And the way that we actually prove it, it's going to be through the affine linear functional, because it's the most elegant. And we had a longer proof, but I think it's too much. So what you basically can show is that every finite dimensional affine subset is closed. And then if that's the case, then every it's like you're separating the space. Like every affine every affine functional in finite dimension, since the finite dimensional slice is closed, cuts the space into two, which means that you can use it to separate elements that have a different value for the functional. And then you have finitely many, and infinite dimension, they have to be continuous, and then you have that they separate points. And then the topology has to be the one generated by these affine functionals, and therefore the topology on the vector space that is generated by the affine functional gives you a topological embedding because it's the same topology. And I think that's the easiest way, and also the most productive way, because once I know that finite dimensional affine sets are closed, I can do other things with that statement.
I see why it becomes difficult in infinite space, because that is no longer guaranteed.
That's no longer guaranteed. And I think I have the counterexample.
I have a counterexample.
Yeah, so this is.
But it's not physical. Was that it?
I don't know. I do not know if it's physical. That's my problem. So it's inside here. Let me see. Let's say AI embedded counterexample. So the thing that this does is you get the set of finally supported probability distributions on uncountably many points.
What do you mean by finitely supported? So that they have a finite support, finite place where they're not zero. That's what you mean, okay.
And the point of doing that is such that you don't have an interior, you kind of have some kind of weird space where you can do things, which is exactly why I don't know if it's completely kosher, completely physical, that is. Then what you basically have is, if you remember what I told you, if you just use the total variation topology, or the topology of L1, it does not make the entropy continuous. So you add another subtopology generated by these sets of like things that converge in a particular way at infinity, so that you actually make the entropy continuous. And you do it by adding this thing, and it would be too complicated even to go through exactly what they are. But that's basically the idea. So you have something that decays in a particular way, and so things that decay in a particular way are in these sets. And so you are sort of taming the blow up at infinity of the entropy by adding these open sets. Okay. And now what you can do here, and so I think it's this is still testing that that the entropy is actually that it's continuous and everything works. So now you take this sequence, and you show that this converges in LS1. But the En does not converge to E0 in the ensemble topology. So now you have a sequence that essentially does not converge with the topology that we are using to make the entropy continuous. And then what you do is now you make a mixture of these two things, and you get some other sequence. And this does converge to easy.
To the same thing.
So it's nasty. The whole thing is nasty, but you have a proof of existence that now this cannot possibly embed in a topological vector space because this thing cannot happen in the topology of a topological.
That's what you said yesterday.
Right, and so this map is continued, but it's not homomorphism onto the image because otherwise you have this thing that would not make sense. But there are many caveats here, right? Because we're working on a space that again, the working on spaces that don't feel physical, but I don't have yet a reason to exclude them. Right. So the idea that I can only make these finite mixtures and I have this space of ensembles, and I can't have possibly mixtures on more than countable things feels very artificial. But
so you cannot mix together more than a finite number of things.
Correct. Or I can only mix them if they have the same bounded support.
But bounded support, it's over n, right? So it means finite support, right?
Yeah, exactly.
Yeah, so it's a finite set where they're not zero.
I keep adding things.
I can only mix finite things.
Yes. So this is related.
Why can't you do countable?
Because this is the space that I am considering. It's a set of finally supported probability distribution.
Right, so they have a finite range over which they're non-zero, but you can.
And so if you mix, infinitely many on a bigger range, you don't go inside the set. You go outside. And so you're saying you can't do it.
And your mixing operation is only going to be applied countable number of times, so you can never get to infinite mixtures.
Well, I do allow for infinite mixtures, but it's the topology that tells you whether you converge or not. Right, so it's the topology of the space that tells you that you're gonna converge to this. So one of the things that you can see here is that, this opens up another problem, which is a problem of completeness of the space. So in a topological vector space, you have a notion of Cauchy sequence based upon the fact that you can subtract one vector to the other. And so if you have a sequence where the differences start being closer and closer to zero, in whatever topology that you have, that's a Cauchy sequence. And you can say that the space is complete.
Every Cauchy sequence converges.
Exactly. So I don't currently have a notion of Cauchy sequence for my topological convex space.
Because you have no differences?
Because I have no difference. And so I'm thinking, oh, maybe there is a way to do it, right? And if there is a way to do it, I'm pretty sure that the set of finally supported probability distribution would not be complete. And I'm pretty sure I will want to say that the space is complete. Right, so it's not absolutely clear whether this counterexample would work. That's where I say I still need to clean it up, because I want to say, okay, suppose that I actually put all the probability measures with finite entropy. Like, can I still do this trick, or it doesn't work, right? These type of things I still don't. Because I suspect that this extension of the topology works because it makes the entropy continuous only on this subspace. If I start putting all the entropies, then it's gonna be problematic.
So, doing a bit of reverse argumentation. So suppose that you can embed it into a, so use your argument to embed it in this span V minus V. Using your couples, multiples of couples. If you impose on that space that it's complete, what does it tell you about the topology, and is that something that is reasonable, the requirement that results from?
I don't know what it tells me.
But that would be the the reverse mathematics way of doing stuff.
No, I agree that would be the thing to do. It's just I can't do everything at the same time.
No, I understand.
No, yes. Because to me, it would be really that. If I had a notion of completeness with that, it's the other thing I would, because connected to that is the notion of a convex integral. And if I have some notion of completeness, it's going to be so much easier to define convex integrals and say that they exist. Because I don't have to worry in how I'm doing the refinement of my integral, of my sums, right? Because I can take any Cauchy sequence that refines things, and I'm going to be fine. If I don't have a Cauchy completeness and I don't know what the Cauchy things are, I basically just say, oh, there exists a way to refine things, but I can't tell you which one it is. I can just tell you, oh yes, there exists. So it's a complete mess. And so I assume that since the notion of convex integrals should make sense in these topological convex spaces, there should be a way to define these things, because it's like you're saying in some way that you have a unique way to extend the mixture to convex integrals with the topology. But again, I don't know.
I should understand it much better now.
It's fun. Like it's like
Really interesting.
Yeah.
Yeah.
And in the same way, you know, like the same thing of the other picture, right? Once you find like this type of thing, and if I find, you know, because this is a dictionary between the convex and the linear, right? It tells you exactly how to translate something from the vector space to the convex space. If I can find something like that for the, as you were saying, right, from for the Cauchy completeness, that's it. And I'm sure that once it's found, it's going to be the obvious thing.
Or at least something that you find physically obvious, or hopefully.
Well, you know, obviously in this sense, right? That you know, the thing here that I had the intuition was that the parallelogram law, it's essentially the mixture here, where there is just a double in the middle. That's it. So that you're basically in the convex space, you're averaging, while in the linear space, you're adding. And I don't have adding, but averaging exists in both, so I'm good. Okay.
But this is like,
Just wondering, there's quite a, so I think you might draw inspiration from what people have done with horse lotteries, right? In decision making, because that is typically.
Horse lottery.
So horse lotteries are typically convex. So the idea is I have a way to have to convexify something. So you have options, right? The idea is I have a number of things that I'm a number of rewards. Yeah. And then of course I prefer one reward to another. That is typically with utilities, as you were explaining yesterday. And then the point is that originally what they wanted to do is have minimax to compare between the two. But for that they need a convex set to do it over. So they can't do it if they have the rewards are not big enough, so they need to have a larger space of rewards. So what would they do? They would convexify the rewards. So they would take convex combinations of the rewards, and that is just probability distributions over the reward set. Yeah. And they would call those lotteries.
But it's finite dimensional.
Typically in well, it could be countable. It could be even probably countable, but and those are, so you have a countable set of rewards, and you would have a horse lottery over that set, and then they say they have preference relations between those horse lotteries. And then there are certain continuity things that, because you can't subtract horse lotteries in very much the same way as you can't respect these things, but you can embed them because of the cancellation property, because they assume that holds. You can embed them in linear spaces, and then you can do stuff there. There's a whole theory of what did you call it? The
Mixed theory.
Yeah.
So there is this book, if you from Dash Perspective by Fishburne. It's just a bit of summary of.
And then I think they also have continuity properties on these orderings. For instance, for Archimedeanity, they need certain continuity properties.
So Fishburne lotteries, Fishburne
Horse lottery.
foundations of expected utility.
Just a bit of summary of this.
Yeah, this is one of the big references in utility theory.
Basically, like my problem is whether they have like what they do in the infinite. Like I need to see what topology they're doing, or they're defining the limit, and that's the thing.
Yeah, when you are talking about the counter example with finitely support probabilities, there was just because it's one of the proof is done often for that mixture space because it's easier. No, it's finitely support. So this is something that is one of the simplest proof uses that as a mixed space. So the element. So and then of course if you want to find something more complex, you need to add some topology. Yeah.
And then there's gonna be the issue that I want my entropy to be continuous, and most likely the topology that we're gonna have is not gonna be that. Yeah, because this is insane to me, like that there is this branch of analysis that also do probability things and so on. So you have the topology and so on. And there are all these people that do even entropic geometry and all that. And then I found that okay, how do I put my entropy in a continuum? I can't find anybody who somehow says this. And I don't, or also the fact that not all probability distributions admit a finite probability, finite entropy. And even there, I found an article that was going through some example, and it was quite recent. And it's not like, it can't be that really, like only people 10 years ago realized that not all probability make it. Can't be like it.
Even Jensen explains that when you go on in the continuous case, it's the definition of entropy is not well defined.
Yes. And the interesting thing is that the symplectic form is actually there to tell you what the entropy is, because it tells you what is the meaning of a uniform distribution. Right? And if you only have a single dimensional manifold, there is no, like you can't do it in a way that it's like coordinate invariant, because you make a change of coordinate, and then the uniform is not the same, which means that there would be one observer that it's preferred because he's the one that is using the units that have a uniform distribution, while all the others don't know, but they don't, right? And the symplectic form is there to fix that, which is again something amazing. And yeah, and even that, it doesn't seem to be well understood in statistical mechanics, which is like the reason why we can do statistical mechanics and define a single Boltzmann distribution of phase space that we don't have to disagree on what it is. It's because we have those measures, right? And again, though, entropy is not going to be continuous on all the distributions, or not going to be exist in all the distributions, and so funny.
Can you define an entropy on the finitely additive one? Because there are finitely additive invariant distributions on the natural numbers, right?
Oh, the discrete is not a problem. Discrete is not a problem. Yeah,
There's no invariant distribution, translation invariant distribution on the natural numbers.
correct, but there is an invariant measure. The counting measure is invariant under permutation.
Under permutations.
Yeah,
Yeah, but not on the translation.
You can't really have a translation. On the integer, you can have a translation. There you go.
Yeah.
Yeah, and so the point is that since you have this like uniform account of states, then you can chop it up wherever you want and have a uniform distribution just by rescaling that. And so now you have a notion of what a uniform distribution is. Because every point counts the same thing. So if you had a space where each point wasn't really equal to the other, right? Because for example, they would have a different.
You have counting measure, but it's not bounded, so it's not a probability measure, right?
Correct. Yeah.
Yeah, so that's the point. You have no probability measure on that. So
you have no uniform probability measure. That's correct.
yeah, but you have a uniform finitely additive probability measure.
When you do the integral, you do the integral of.
Sure, that's a mathematical trick, but I'm just saying that that the problem is countable additivity. You define that. There are countably additive.
Okay, so if you're talking about the principle of indifference that you want to have a uniform, I agree. Yes.
Okay.
That's not the problem that I'm talking about.
Okay.
Like even if you have a bounded interval from 0 to 1, right? Because you are on a continuum, you have no notion of uniform because I change the x and I distort that.
Yeah.
Okay, so the problem is really the continuity more than.
Then the countable.
Then of course, if you have countably many and you want a probability measure, that's not gonna exist completely. So
Yeah, I agree, okay.
anyway, Renyi entropy that
Yeah.
you want to show that,
Yeah.
can you share directly?
Yeah. I don't think we should use his.
Oh, yeah.
That- I know, or you could, yeah, either that or join, you have to join Zoom either way, right? So you can join Zoom from there, and my laptop is projecting whatever's on Zoom.
Even though in Zoom, I don't see anybody.
There have been people on the live
Oh,
stream.
there are a couple of people on the
There were
live stream.
5 so far on the live stream.
We should.
More there, yeah.
For
People
the
that
live
like
stream, we
us.
don't know, yeah.
Hi, everybody on the live stream.
You would see chat comments on the live stream.
Yeah, yes, I have to chat in case anybody says something over there. Oh, yeah, might be. It is spring water from University of Michigan.
You got a river here.
Yeah.
I don't know that, did you? Are you getting invited to become a panelist? You see. You sure or not?
Okay.
You should, I keep clicking change, you can try it, change all the panel. I mean,
We should get a prompt with that.
yeah, you should get a prompt.
Oh, there. There was a major delay. That is.
Okay, so I think I will skip this about, just the subject that for now probably you know well. So I skip this part about lower precision. And also this connection with epsilon contamination, probably is not relevant. Just give you some concept that what could be used. Yes.
Since you guys were talking about what we could also do together later, if you want to prepare, or maybe you already have like a mini course on imprecise probability, we could do a live stream on that at some point. Might be stuff that is interesting to other people as well. Okay, so
So just focus here on finite possibility space and assuming that the element of the mixed space are probability, because I wanted to understand if there was a notion that is of fraction capacity that is already known.
Yes.
So this was my idea. So the fraction capacity is defined as the folly. So since we are in the finite case, just a max.
Okay.
Over this, call it the weight W instead of P. Okay. So and this I want to be the fraction capacity of P0 with respect to P.
So that's a single point.
Single point for the moment, and then the extension to the convex hull, it's easier after.
So C is the set of all probability density function or probability mass function?
Exactly. This is the weight, this is all the probability mass function, the simplex, probability simplex, all of them. So this is and you have these constraints, and in this case, if you represent this probability as a vectors, it's element-wise constraints. Okay, so for fixed W, okay, so this is what we call it an epsilon contamination. So you are taking P0, this probability that you care about, okay, and you are contaminating with respect to the other distribution. Okay, this is a cradle set. Okay, for a fixed weight, actually, the epsilon is usually 1 minus W, but it doesn't matter. Okay? Okay, so this is, it's called epsilon contamination. So you take a distribution, okay, you perturbate it by doing this contamination with all the other distribution.
Okay, so you're basically taking the simplex around the point.
Exactly. Exactly. So this is, for instance, using in robust statistics. So you have some precise distribution, and you say, I'm not sure about P0, I'm going to perturbate. Okay.
So I use that function in a bunch of different ways.
Mm-hmm. So usually that's why you do something different. Usually, in the you can see most of the case, for us, we fix W and we move this in somehow. Is this what you are moving here? That can vary here. Mm-hmm. Instead, you fix this and this. Okay, these are your, and then you vary the Q and W. Okay, so what I will try to do here is simply try to understand how to write this in a linear programming as a linear programming problem, and then see if it's something that we knew. I was trying to do it. Okay, also because okay, first of all, let's check that this. This one is easier, but the other one with the complex.
Sorry, but in a sense, you're looking for the smallest epsilon, right? So the least contaminated model.
Yeah, it's the other way around.
It's,
yeah, you work it. Yeah, in fact, so the other thing is that Gabriele has it's basically to show what happens when you, for instance, if this is the joint distribution and this is any conditional, okay, then you get that this is maximum weight, that you can get correspond to the marginal probability, And so it's the other way around because
So if I went to 1 minus W, I would get the lower probability
Exactly.
there, right? Yeah.
Okay, so to do the linear programming problem, I was trying to exploit the fact that we are in this finite dimensional case, so I can write Q.
But here is still using with 1 point versus 1 point.
Yeah,
right?
yeah. The extension to the complex solver, I just do it later because it's with this connection with the NI entropy. It's actually quite easy. Just because the convex solids, you can write it as a linear constraint.
And right now you're assuming that the full ensemble space is a probability.
Yeah, because I wanted to find this connection with something, in probability. So I think that I could even generalize here to the fact these are not probability mass function or something more general, but still probabilities. I wrote this Q as a sum over the extremes of the simplex, okay, and then so in this way can write this problem, okay, as the following. Okay, so you maximize W as before. Now, basically, I use, so W is the same as before. I replace that 1 minus W times Q with this combination, exploiting this, where the sum of these now is not 1, but is 1 minus W, because this is what again. So in this way, I just wanted to have everything linear in my variables that are these and these. And then I do, I can do the same for this. Okay, same stuff. I write as and then you end up with this expression. Okay, yeah.
The dual form.
Yeah, I actually didn't write it well, but so what I simply for is say, okay, look, you have this. I can call it this beta I. Okay, and then I wrote basically I wrote this. Sum of beta I times this equal to P, where basically what you get, since this is it's positive for each because it's an element of and this is the mixture for the Q that can be everything. So this can be any number, and so that at the end I can get this beta ID needs to be greater than this because this can be in the minimum in this constraint, and I have this. And then I do the same, doing this game of writing my P as a function of the extremes. With this here, and at the end, basically, this simplify to basically to this expression here. Okay, so at the end you get that you want to maximize this with the constraint that Pi, that is this, the element of this, is greater than W times P0. Very
It's
simple.
just a pure multiplication thing.
It's right.
A common multiplier.
Yeah, so it's super easy. And of course, when this is 0, so when outside the support of P0, this is trivial, so it doesn't have any constraints because this is always greater than 0. And so at the end, I only care on the constraints only active on this set, so where the support is strictly greater than 0. And then basically at the end, what you have, you can because of this, you can divide now in this set, you can divide the pi divided by p0i, and then you get this. So by swapping. Okay. So it's this simple stuff. So at the end, the optimal solution. So since you want to maximize W with this upper constraint, okay, the maximum is this, okay, and then you get this. So you had basically that in this case, the fraction capacity is the minimum over the I in the support of P0 is pi divided by super simple.
Yes.
Okay. And then I thought, okay, well, must be something known because it's super simple. No? And then I went to check, and I remember something similar. Okay, these are the examples that you give. For instance, if pi is 1 divided by, so it's the dice, and this is 1 on number 3, you get just to check. Okay, these are all that is more interactive. Something okay, so this is the connection that actually we care about. So the RNI divergence is defined as the divergence between P0 and P, in this example where it's R is a probability mass function, is the log of the essential supremum, which is okay. The essential supremum is the supremum over the support. So with the elements that are not 0.
Yeah. So you eliminate the zeros where it comes in.
It's this.
But it's supremo of, oh, okay.
Support.
Yeah.
Okay. So it's like you can see it's a probability arch.
Yes, you're removing.
So you take the maximum over the I that in the support. So the element of P0 that are different from 0.
Okay.
Okay.
And we don't have a check that the PI has to be different from 0?
This is a great, no? It's weird, but it's not. Okay. Because actually, so what you don't want here is to have 0, because log of 0 is minus infinite. It's not defined, no?
Okay.
And then you plus infinite is fine. Okay, so then the other way around is fine.
So that is a really divergence.
Yeah, and so you get this log of log of max, and then you add here. Remember
How do you find
like,
really
this is
the
completely
convergence?
curious.
Because you have an expression and then you have to look where does it occur? How did you find that?
Yeah, you can. I have a reference.
Okay.
Yes. I know. I think I gave you. I don't remember if it's here, but yeah, there is a paper about this. And so basically, this is defined. You see, so basically, you need to swap it. So your solution. So I'll go back here.
Okay.
This one you can see, yeah.
So that's the minimum of that. That makes sense to
Yeah.
me because you're basically, you have a distribution and you have another one that is a little bit below, and so you're finding like how much you can fit, and that's gonna be given by the maximum value. So yes, that I understand. Now the inverse is now the maximum of those.
Yeah, because basically here you are minimizing this fraction,
Yes.
and the minimum, if you swap the fraction, is going to be the max.
Oh, okay, sure, of course, yes.
So
Okay, cool.
minus the logarithm of that
And yes,
is the Régnier entropy. So
this is
you have the exponential of minus the. So it's a relation between the exponential of the entropy and the.
there is this log you don't have. It's the entropy, there is always a log. And this is actually the entropy with this there because it's defined by an alpha. Okay, the standard entropy has alpha equal to 1 or 2, I don't remember. And this is the alpha equal to infinite.
Okay, so let me understand. So now I don't care that the maximum might have a PI that it's 0.
Yeah.
Because then W star would be 0 anyway. And so
So basically, so these allow us to define your orthogonality. Okay, it's the same way you define fraction capacity. Your fraction capacity, things are orthogonal is W is 0, is correct, no?
Right, because you don't have any components, so
Okay.
they're separate for in our
In
case.
the Renai, when this is infinite, is the definition of orthogonal in the Renai thing. When the entropy is infinite, there is the definition of the divergence.
That's separateness for us. So what you're basically telling me that the Renai entropy picks separateness instead of the orthogonality.
So basically, if you go to that in that paper, there is a section about what they call it how to define mutually singular distributions, and they do it with this prove that every Renai entropy is infinite when they are mutually singular. And so basically, yes, you can see the y because it's 1 divided by your.
Yes, exactly. So you basically say, no, I want it to be infinite because I don't want to think it as a function. You want to think it as like on the extended real line.
Yeah, it's a divergence.
Yeah. In the same way that you do it for measures, you want to be able to say that the set, the measure of the set is infinite, and not that it's undefined.
Exactly. And in the more general case, that is the one with the convex R, it's very similar because basically the idea will be, so you write any element in the convex R as a convex combination of the vertex of the extreme of the R for A, whatever they are. And in this case, as before, this is sum to y minus W, and this will go to sum to.
Wait, sorry, I'm still digesting the thing before.
Sorry.
Because okay, so the Renyi entropy is getting two things. So it's like a relative Renyi entropy that the Renyi divergence.
It's a divergence, it's not an entropy, yes.
Oh, okay. So it's the divergence that you get from the Renyi entropy in the same way that the what's it called? The KL divergence, you get it from.
Yeah. So this is interesting because basically it's easy that actually, what you are using, you are defining a divergence, the other way around, but you are defining. And I think the only thing that I think would be interesting to understand the effect of the zeros and how if there is any difference, in the more general case, what you deal with the zeros and you are to deal with the infinite. So basically the role of the supports of these things. I think that is especially when it's not the simplex of probability. But I guess in that case you cannot define this. But
because in that case you wouldn't be able to find the Renyi divergence.
Yeah, because you can. This doesn't make sense because this is on the element of your
of the simplex.
Yeah. So in general, it would be I don't know A and B. Or, I don't know. We cannot define a fraction.
Okay, so you're basically saying that this reduces to the Renyi divergence if you are a simplex, but then we can do it in now more general case.
Yeah. Actually, I think this is something. Is a nice result that is interesting, basically to define this divergence in this fraction capacity way that allows you to extend outside the probabilities.
Cool. If you want to do a paper together on this, that's certainly interesting.
But it would be interesting.
I don't know. Yeah.
So now you're going for the more general case, and that is
the more general case is basically it would be like the convex hull. So for each element in the convex hull of A, remember the fraction capacity of the set. Actually, I've already set R. So
that's the convex hull of A.
Yeah. So I have R that is the set inside the simplex. Okay, and
it's convex.
I take the convex hull, it is convex.
Which is why you can do a linear program.
Exactly, I can do the linear program because I can write any element in the convex set R as a sum of these extremes, and so in this case this will be convex combination, but in this case since this originally was W, they sum to W and not to 1. Okay, so it's the only difference I do because I want everything to be linear in my variables. So I don't want products of variables here. This trick basically I transform the unit here in W. And then here you can see it's easy because it's the maximum over W over the weights for the general element here over the weights for the convex combination that give me the element of the convex R of big R. And so this is the problem. So then you can do exactly as before. And it's very similar. And proved. So at the end, basically what you can prove, but actually I didn't prove because it seems to be obvious. Then at the end you end up with this. So you have the so your solution or the optimal is the max over the beta, the max over I is the element of the distribution as before. So you have this other max that was not there before, and the max is over the convex combination. So basically you need to pick an element in R, okay, in the set, and for each element you compute the RNA dimensions, and then you take the max. This is, and then you get this. I think the other one. And yeah, so it's the way you start. So it's very simple. So it's just, you know, because at the end, what so replace P0 that was here with this expression. The only thing that is a bit tricky here that I didn't think about is that before there was that essential supremum, so the support. So how you define the support in this case? We didn't think about, but I guess you should be able to define it in a way that, I don't know, maybe if each fraction here for a fixed element, you know, the support. So you need only to compute on that support. Not sure, but this is the only thing that I didn't think about. So if, you know, if this all positive, then it's still. Yes. And I don't know if I have the reference. And the reference with that paper, but yeah, I can share with everybody.
What you're actually then doing is taking the infimum of the linear divergence over the set.
In this case, it would be because it's the mean.
Yeah. And does that mean something to you? Because if the callback, what is the callback libeler over a set? It's also the infimum with. Yeah.
So is there a way to characterize the point that is the closest at this point?
You mean the point is this? You mean the solution, the one that gives
The solution.
Well, that's the one that minimizes the Regnier divergence.
Right. That's true for both the set.
Yeah, because you can see it's trivial. The convex combination is in the numerator, no? So it's really it's just trivial.
So your fractional of the set A is the exponential of minus the infimum of the Regnier divergences over.
Yeah, the only thing is a bit tricky is with the support, because the support of a single one was easy, no? But now you have I don't know if you have like a set, convex hull on some element that maybe have zeros in different places. Probably that is a bit tricky. I don't know. But yeah, something to think about. I don't think it's.
Okay, really cool. So we are saying that if we have our simplex, and then we pick an E, and then we pick a horrible mess of things, and then we want to find essentially in this sense what is the point here that it's the closest to this guy, right? Which is going to be this guy.
Convexify it.
And it's going to be a convexify and get the one with the lowest Regnier.
The smallest Regnier distance.
Yeah, you can see it here. No, this you do the minimum.
Because I want to be, in a sense, to have this as the representative of this guy in this set. Because when I do things like conditional probability, I suppose that I know that it's this. But then I want to essentially, yes, I would like to get the expectation. How did it work? I don't remember what was the direction. If I have the expectation of this guy, knowing that I'm here. Yes, like so. The basically is that right. So if I have this point that represents my probability distribution, right, and then I want to be able to say I project to a set in the same way that I would project if I were stripping the support. So if you imagine that I have this probability distribution and then I take this support, I want to be able, once I project, to find this guy because it's the one that would give me the highest fraction capacity, the highest fraction. And so here I want to be able to say the same thing. So I have this, but then I want to restrict myself here. Then I want to find the one that has the highest fraction. Then what you're telling me is that I have an equivalent way to say this, which is it minimizes the Renyi divergence.
Yeah. But be careful, because then in this case it's true because we are in the simplex.
Yes.
Case. And the more general case.
Right.
Are you guaranteed to have a unique point that is closest? So does it actually give me a pseudo distance, this Renyi divergence?
I think so.
And then it would actually be accurate to say it's the closest point in that distance, because the geometric distance is not correct, the correct one.
Yeah.
Okay, and then there might be actually like a unique closest point.
And in the finite dimensional case, since the other entropy tells me that any, we still have to finish it, but I think that it's going to work out that any finite dimensional ensemble space is bounded. It means that we can find a simplex that contains the whole thing. So now that would be, of course, the probability distribution in terms of these pieces that could be, these points would be outside of the simplex, but it's still a representation. And as long as this minimum distance does not care about what the representation is, then it would still work. In the infinite dimensional case, of course, I have no idea that that would work, but.
And the supremum would be a maximum. There's not just a maximum, there's like an arc max, like I know the argument that maximizes. Expression.
It tells you what is the element of in the set. Yeah, the nice thing, yeah, this is something interesting, because at the beginning, I started off, I was curious, I brought the linear programming problem at the beginning, because I was but to understand if the max was in the border of what you call the capital A, but it's not, and then it can be in the center, and so this is something that it's
Yeah, because it depends on the shape on the other side as well. That's the thing that is tricky.
Yeah.
Because you might have a pointer that is closer, but then the other point on the other side is has the other part that is actually farther from the point. And since the P is the ratio between this distance and the whole distance, if you maximize on the other side, you still get something. Yeah, it's weird.
Yeah, it is weird. Yeah. But yeah, I mean, it's nice that it's a linear programming problem because, as I said, so for instance, if you needed to extend this with the W being a probability measure on some, space or some subset, or some element of a sigma algebra, then you can still try to write these problems, and then it will be infinite dimensional because your variable is going to be measured. Okay. But then maybe you could try to approximate it to have an intuition of how this behaves in the infinite dimensional case. Yeah. So this is something that at least it helps to have an intuition. So
Yeah. Yeah, everybody has different intuitions. So again, if you have more ways to get to the same problem, and say, oh yes, you can think it in these different ways. That's
It's really cool.
so. But then the thing that confuses me. So nothing from 2 on really used any of the stuff above, right? Am I confused? Or?
What do you mean?
So if you So this, go when you start. Okay. Right, so here, right? So when you have, so when we're defining all of this, so we just have a simplex, we're just going to talk about probability distribution. This has nothing to do with the epsilon contamination, or does it?
No,
No, that was.
Okay.
no, just to give you some, things that we use, some background. And also, the other things that when you discuss about conditioning, you say, oh, look, if this is a P0 is a conditional of P, you get this is maximum. And then the other case where they are orthogonal, you get the W0. Okay, so there is an operation that does similar things in precise probability. That is what's the name? The regular state, no, sorry, I've read it here. So the condition that is defined as our condition or the bonus.
What general space rule is that?
So basically, either you do the base rule or you assume the Bacchus set. It's not
The regular.
the regular. It's not it's the regular extension. Yeah. So basically, it's you in that case. If you want to talk about conditioning, you get that there is an operation in precise probability. That tells you basically, when you do a base rule, okay, if the denominator is different from zero for each p or set distribution, you apply, you do base rule for each p, and then you can take the max or min of whatever you want to compute the integrals. Right? But if you have zeros, you cannot apply base rule. In that case, a way to find something that is conservative is to take all the set of probabilities. It's what exactly you have, because when W is zero for you, basically means that you're using all the Q's, the distribution there to do the condition. So your set of probabilities is everything in that case. Okay, so this is the connection in that case. So maybe useful when you think about conditioning. Okay. Because the condition is well defined only when you don't have zeros. When you have zeros, you have to assume something, if you want to do something, be able to do something, and this is our conservative way. Basically, if you cannot do condition, you take all the space, all the distribution.
Scheduled to break 22 minutes ago.
Okay.
Before our sort of final planning discussion. Given that there are Zoom, I didn't stop us to keep us on a schedule. Down a bit. Wouldn't mind standing up for a few minutes.
Okay, let's stand up for a few minutes.
The coffee did appear. With some cookies if we want.
Yes, that's a cookie.
Back at 4:15 and
Okay.
there are a few people on the live stream, so in 22 minutes.
start here. Sorry about being late. We got into a heated discussion. I would resolve at the end. Okay, so what do we want to talk about now?
We said this is gonna be planning further work,
Oh, okay. Planning further work.
so
Yes.
I mean,
There anything left in the list or?
Yeah, there was something about extending it to infinite dimensions that we didn't address, but that would be further work then.
so we did discuss.
Yeah, but defining the background in the finite dimensional case, there was the reflexivity of topological vector spaces.
Not that we resolved it, but we discussed this for now. This we discussed.
How is the cancellative property justified is something we already discussed, I
Yes.
think.
Don't anymore, but that's okay. Reflexivity and.
So the background in the finite, this we didn't have yet, right? So it's you have a star against the how is a property justified, doesn't have a star and it should,
Oh, yes, did I
and then the
put it
one
in the
below
wrong
that
one?
shouldn't.
Yeah, I just did it. Well,
So I think we basically also we're discussing already the defining the background in the infinite dimensional case because, well, I guess I don't know if we did or not, but the point was that when we are defining, oh man, I have to go back. What was the symmetry of evidence?
Mm-hmm.
this is evidence of symmetry.
Right, which is the one that tells me the space of possible probability doesn't pick one.
Mm-hmm.
And then in that case, what we basically need to do, at least when I think about it on the space of probability of or an ensemble, there has to be a topology on that thing. And the set of transformation has to be continuous.
Continuous with respect to the topology,
Yeah.
yes.
And then we're gonna have one parameter groups with generators.
Mm-hmm.
And then the Lie algebra tells us the Lie algebra of the generators.
Yeah.
And then in principle, it should tell us all the symmetries.
All the symmetries, yeah.
And then we should be able to pick out.
An invariant cone of the symmetries.
Yes.
So that idea could be extended also.
So actually, this might connect. So in quantum mechanics, so if you remember, I was saying how the space of the Hilbert space basically have this problem that you can get on physical things. You can get sort of sequences that converge to a state, but the sequence of the expectations do not converge to the expectation of the state. And this is because the observables are not continuous. So one way we were thinking to amending Hilbert space is by saying that the observables have to be generators of one parameter group, and they have to be continuous. This basically makes it so that you're going to constrain both the topology and the space of functions. Because if X is self-adjoint and continuous, it means that also X squared is self-adjoint and continuous, which means that any X to the N is self-adjoint and continuous. If P is self-adjoint and continuous, P to the N is self-adjoint and continuous. And if X and P are self-adjoint and continuous, Xn times P to the M is not self-adjoint, but it's still continuous and it's adjointable.
Yeah.
And if you just say then the topology has to be the one generated by this, by these, the continuity of these, and you are complete in all the Cauchy sequences generated by that topology, you get the short space.
Oh, you do?
You do, because the Schwartz space has a topology generated by the semi-norms that are from essentially from XNPN, and it's complete in that topology. And when you get completeness, you get one thing. It's
Unique completion. It's a unique completion.
Yeah, because the completions are unique.
But this is not a metric topology, right? Or is it?
This is a metrizable space.
It's metrizable.
It's not a Banach space. It doesn't have a norm.
The what that?
It doesn't have a norm.
It doesn't have a norm.
There's a
Okay, but
distance
it is
to the
a,
band.
okay. but
It has countably many semi-norms,
Okay,
and then you can sum all those countably semi-norms, and you get a metric, but it's going to be a completely useless metric.
Yeah,
okay.
if you want to
You
measure
can work,
the,
you can work with a family of semi-norms.
if you want to measure the distance from zero, I think it's just not homogeneous. So I mean, you have a metric, right? You can measure distance. Naively, you would just measure the distance to the origin to get a norm, right?
Yeah.
And that norm would just be not homogeneous. It's not a norm. Does it make sense? I think you get at least a metric, so you can measure distance, but it will not be homogeneous. If you measure distance to the origin, you could all get a norm, you don't have a Banach space.
So in the elements of the Schwartz space are these infinitely differentiable functions that go to zero quickly.
Faster than any polynomial. Yes.
Exponentially.
Yes.
Minus squared. Or
Well, it's not quite exponential. You can have something that's a little bit slower, but the point is that if you multiply by x, the integral still converges, so it's faster than.
faster than linear.
Yeah.
Polynomial.
And this also means that like it's not like the what's it called, the Hilbert space where each vector is an equivalence class of wave functions up to a measure zero. It's one function, and so the probability density at each point it's well defined. It's basically what a physicist would write, and all the Hermite polynomial, the Hermite functions that are the solutions, the eigenstates of the harmonic oscillator are Schwartz, and it's a countable basis, and so they generate all the space.
Okay.
And what we think is this should be kind of how you extend it to all the other spaces. You basically get the generators and you get your Poisson brackets. That defines essentially the core observables that you care. And then you just generate the topology there and you close. And that should always give you a unique thing.
Okay.
Can you say again? So you start with the space, and then you said you wanted the.
Yes, we don't want.
So what is the thing that it doesn't satisfy?
So for any unbounded operator in a Hilbert space cannot be defined on the full space.
On the what? On the?
They cannot define on the full space. The domain of an unbounded operator cannot be the full space. If you have a continuous linear operator that is defined on the full space, it has to be bounded.
Oh, yeah.
Continuous and bounded is just the same thing.
Same thing, all right? Yeah. Well, it's actually Lipschitz continuous, right? Because you have an operator norm and
Yes.
on a norm space, right?
Yeah, the Hilbert space is a norm.
Yeah, it's norm. Yeah, okay.
Because the
Continuous
space is
continuous
generated
and
by.
bounded is the same thing.
Yes.
Not just for linear functions, for homogeneous functions. It's
At this point. But the point being is that it's not only that it's not defined on the full space, it's not even continuous. right? So you can have a sequence of states that converges in L square, but the expectation of the operator does not converge to the expectation of what of everything. And so you can construct unitaries that do weird things. So you could have a wave function that have a bounded variance. Then you evolve it through a unitary, and after like a time step, you have infinite spread. And then you wait for the next time step, and you go back with finite variance. You keep oscillating between these two things. Like you can construct a lot of these things that make absolutely no physical sense.
Paper on that.
So for self-adjoint operators is another characterization of whether it's continuous or not, or defined on a full space, which is every self-adjoint operator generates a unitary transformation. And exactly when the unitary transformation is differentiable with respect to its parameter everywhere, then this is continuous. In fact, the domain of the self-adjoint operator is exactly those states where you can differentiate with respect to result. So if you want to think about the unitaries instead, it's about differentiability.
And being continuous.
So this generated by means that it is the exponential.
Yes.
Of that, right? Okay.
And so what we want to basically do is do the thing. Oh, and this basically also means that when you write the commutator of x and p equals I h bar, that makes no sense because on one side you have the identity operator, which is defined on the full space, while x and p and therefore the commutator cannot be defined on the full space. So that equation is literally not true. You would have to say, if I restrict that on the domain of the other, then they're the same. Right? So you're basically trying to do something with this space, which is not the natural thing that you would do as a physicist. As a physicist, you would like to think of the wave function as a function. I give you an x, I get a number. A vector in a variable space is not going to give you that because it's never at every point is not defined because it's not defined on a set of measure zero, right? While if you say, no, I want these operators to be continuous because I want my observable to be continuous. I want that for a small change of a state, I have a small change on the expectation. I would say that if you do that, it also means that when you write your one parameter group and you make the derivation of that with respect to parameter, that derivative is always defined in the whole space, which again would make sense. It's like your revolution is literally differentiable, not differentiable in a dense subset. No, it's just differentiable. And by assuming this simple thing, you actually even get disclosure on the x to the m, p to the m type thing. You get all the powers, which also means you're avoiding the problem of the entropy not being well defined anymore. Because if you do this requirement on the mixed state as well, then the probability distribution that you're going to get are still going to be things where all the expectations of all the polynomial opposition momentum is going to be finite for all your statistical mixtures, which means when you go and try to calculate entropies, then the tail is going to go down fast, which means the entropy is going to be well defined. And the entropy is actually continuous on this topology. Because at some point, you're going up P log P, at some point you are dominated by some polynomial and you're not going to have it.
But at the end, what you wanted that is like point evaluation are continuously enough functions. It is that you are saying. Because you said that you cannot do that with the, for instance, the density function is not a function because you cannot evaluate it. Is this that you need? Or
I'm saying that all these things are the same thing.
So
is the idea that if you work in this Schwarz space, it works? Is that what you're saying, or is it, am I completely misunderstanding what you're?
Yeah, so there is a guy that we met that has been doing this for 20 years. He's a mathematician from the south of Italy that has been developing a whole theory on Schwarz spaces that he claims is a lot nicer. So we're working on him on some things on this. And what occurred to me is that, okay, Schwarz spaces are not going to be useful for everything. I'm doing a field theory. Of course, I have more. I have numbers of particles and so on. So Schwarz spaces is not going to be. But the requirement of saying that all my operator needs to be continuous, and in the case that you say the operators that I'm interested in are position and momentum, and I have to be complete in those, the fact that that assumption that it seems so basic already recovers the Schwarz space, which is a much nicer space to work with. It's sort of a strong tell that this is what it should be.
Yeah. Okay.
By the way, how do you, okay, we restrict the Hilbert space, right? We have something smaller than the Hilbert space.
Yes.
We throw out some pure states. How does it work? Like what, I'm wondering what density, like what mixed states, density matrices you throw out in a process, because the Schwarz space still provides me with a basis.
Yep.
And if I would allow all convex combinations, I would again get the same density matrices, right? So because
Well,
it's a basis. So I guess
what you're gonna put is the same constraint that you put on the space itself. You want your operator to be continuous, right? When you're
but the density
acting,
matrices are all continuous because they are bounded.
what?
I mean, the density matrices, shouldn't they all be?
No. When you're applying the X and P's on your density matrix, right? Now you are generating a transformation on those things as well.
How would you define the density matrix as a self-adjoint operator on this space that traces to one? So the trace is also defined for all those.
Yeah.
So that's the definition, self-adjoint and trace to one.
Yeah, it's the same definition.
Same definition. And then since it's going to be continuous, because
Right.
right, it's continuous operator again.
Yeah,
right?
it's a continuous
So
operator.
self-adjoint continuous.
Then I truly don't understand which ones we throw out.
You're throwing out the density operators that would not, first of all, they wouldn't map Schwarz to Schwarz, right? Because they're not self-adjoint on the Schwarz space anymore. Like if they're self-adjoint on the Hilbert space, they take an element of the Hilbert space and give you an element of Hilbert space. Some of them I'm gonna take a Schwarz function and give you back a Schwarz function. Okay, so those are the ones that we want. And they have to be continuous.
I'm thinking continuity might already like, because density matrices are already bounded. I
Yes.
think they will all be continuous anyway, so that is not a criterion that would exclude some. So the
Very good,
excluding
okay.
criterion would be mapping Schwarz to Schwarz.
Schwarz to Schwarz, and then I don't know if there is an additional condition that you want the expectation, like the X and P's to be well defined on those. I think maybe that once you map Schwarz to Schwarz, you are gonna get them. I don't know, because it depends on how you do the convex combination. So you might have to throw out convex combination that make the expectations of
So all finite convex combinations
not a
have to
problem.
be,
Yeah.
obviously, so naturally, I would only allow those infinite ones that the topology tells me to converge. And with that, shouldn't be enough.
That I think for which the expectation of position and momentums are or the
The
monomial
same
position
thing,
momentum
this
are.
is where the topology comes from anyway, right?
I
But
don't know.
it's a topology on the.
Oh, right. Oh, yeah, okay, so you said continuous, but continuous on the Schwarz topology is different than continuous on
Yeah, right, we
right.
go one level up, we go on
Yeah.
the space of matrices.
Yeah.
I don't know, necessarily.
Okay, so
Operators,
Yeah.
that would be an operator norm, but usually I would inherit that.
no,
from-
I think it's gonna be so. the fact that you're continuing in Schwartz means that you are continuing in L2 as well, because it's a subtopology.
Yes.
And so you have a bounded operator.
Yeah.
But continuous in Schwartz means more.
You mean continuous in Hilbert's?
No, continuous in Schwartz means more. There are more sets.
Where can I find information about these short spaces?
Yes, there's so much information about Schwartz spaces.
Yeah.
You can even start with
Is there like a
Wikipedia.
basic textbook that you would?
Yeah, there are many. Like I studied them when I did the signal processing in.
You mean, yeah,
university.
yeah, so it's like
That's
distribution theory.
Yeah, it's distribution theory. And so yeah,
Then to distribute all that stuff. Yeah, Fourier.
Yeah,
Yeah.
yeah, it's like
As
Yeah.
much.
Now, in fact, I was also thinking it's if before going to spores, if you can do something with reproducing kernel Hilbert spaces. So they are Hilbert spaces. They have this property that point evaluation are a continuous linear function, because it's one of the properties you mentioned. No? And of course, they are not equivalent to spore spaces, but they have a nice property, like for instance, the polynomials are a basis of those.
What space is this?
Reproducing kernel Hilbert spaces.
Reproducing kernel.
Reproducing kernel Hilbert spaces. So there are Hilbert spaces where the evaluation function are continuous linear function. And they have some property, they have some analogy, and yes, but they're also again related to signal processes and statistics. So they're all, and they have some, you're still in a Hilbert space, but then you have this property that for its polynomials. Now for that, they're orthogonal and for some probability distribution, and they're on basis of this space.
so. There are other like approaches of people with Greek Hilbert spaces, and they try to do a lot of things like that. But it seems that with this requiring these operators to be continuous anyway, it's the thing that you want to have physically. And once you do that, you get a snowball of both these other things. So again, I'm trying to find the things more than the mathematical convenience. I'm trying to find the things that can be justified physically. And the continuity means, as I said before, small changes in the state means small changes in the observable.
Yeah.
Right? And the completeness means that if you have if your evaluations evaluate to something, that's a space that should be there, right? And
So, okay, when you say small change in state leads to a small change in observables,
Yeah.
we're actually not, we are thinking about the matrix elements, right? I'm taking the expectation value of that operator in some state, or it's actually in any state. And that thing is a real number.
you
And
can
that
also
is-
define it like that, yes.
Yeah, because like the output, the wave function after applying X doesn't mean anything, right?
Yeah.
I don't care.
Yeah, that's kind of a problem.
Okay, so, but this is really the one that we want, but it should be equivalent. It's that continuity of the expectation values that we really care about.
Right, so
But it should
when
be
we
equivalent.
look at in our framework of thinking about statistical variables, those statistical variables have to be continuous, so therefore the expectation is to be continuous. And if the operator is continuous and of course the inner product is continuous, you get that.
This is okay.
Yes, and if your expectation is not continuous, you're not gonna get a continuous self-adjoint operator. So the point should be that, so what we're trying to understand is whether these arguments can be generalized to just the notion of continuity that we have in ensemble spaces and to classical mechanics, because I will want to be able to say something like that in classical mechanics as well. The thing is that in classical mechanics, of course, momentum is just another thing. And so you don't really have a Schwartz space in the sense that you get the decay that goes to infinity, you go faster than any polynomial in every polynomial of position of momentum, but you don't get the infinite smoothness. And I don't know at this point whether that's a problem or not. And it may be a problem if I want to think of these as generators, because the generators for the probability distribution, we're going to be the Poisson bracket with the one thing on one side. And that thing might not be differentiable if that thing might not be well defined if the distribution, the probability distribution is not differentiable, because then what happens is that you are applying a differential operator on a function that it's not differential, right? So I do not know how and how these things work exactly in classical mechanics. It's one of those things that sometimes it's easier to do things in quantum mechanics, sometimes it's easier to do it in classical mechanics. And this is where I don't know exactly what, but
So the differential operator is because in the Poisson bracket you have differentials, not because P has anything to do with the differential.
correct, because P itself is not doing
Yeah.
but you have actually a differential in the Poisson bracket. And I don't know if this may be connected to what Marcel was presenting, where he has this thing where he has both the operators of the position momentum, but then also the derivative position and derivative momentum. So and then he was doing stuff with that. So I don't know if that is the correct space for the Lie algebras in classical mechanics. I have no idea. But it would connect to the problem of defining these backgrounds in infinite dimension, because depending on the classical and quantum, we have to understand what are the correct Lie algebra that actually covers everything. And last thing, then I'll shut up. This idea of fixing the operators and then finding the space by completeness, to me sounds very much like finding these transformations that give you the
Background?
yes. Because in a way, I'm basically saying, these
What is
generators.
allowable?
Yeah, what is allowed? Yes.
What transformations are allowable?
Yeah.
Yeah, that is typically what in the simple examples that is so in Hilbert space it's the unitaries and it's the permutations.
Right. And so here we're restricting a little bit more, because these, like all the transformation on these that are generated are going to be unitaries, but we don't allow all the unitaries. So you get a nice space, but you have to keep in mind that we are ruling out some things that other people may want, but which I don't think actually are things that we want. So there is this example, classic example of operators that are symmetric but not self-adjoint. And the classic example is the half real line. So you have from 0 to infinity, and then the position, the momentum operator is not self-adjoint, but it's symmetric, right? And you can see that momentum cannot generate a one parameter group, because yes, you can translate in one direction, but you can't translate in the other. And to me, it feels like you are actually breaking the whole structure. And the only way that we really have like this type of thing, typically it's because you have some radius, and then you actually have something at 0, and you have another coordinate that does this. And so if you don't get the full space, so then of course you're going to have problems. And I think the fact of the lack of the self-adjointness of R is just because you don't have the full domain, and of course you're going to have problems. And so you might need some other boundary conditions and so on, but clearly the translation does not work.
If you do it on a finite interval, then your like canonical momentum operator also has many different domains on which it is self-adjoint. And I think from examples that I've seen is basically you have an interval and you want to shift and you have kind of different boundary conditions, which is either you make it a circle,
yeah,
you shift like that, or you just say on the boundary it's always
Zero,
I
maybe.
think it's 0 or something like that. Yeah, so it really it's about defining how the group acts to solve the whole domain issue. So pretty sure this is the correct connection.
But again, I don't think it's gonna be a problem for you because you just say, this is the background in this case, this is the background in this case, this is the background. I'm not going to claim that I can tell you what are all the backgrounds.
Yeah, no, the idea is that background is defined by the allowable transformations. And so once I have those, that would be it.
Yes, it's the only physics, the only thing that is physics.
Yeah, so I think that was what I had to say about it.
Yeah.
And for field theories, it would be understanding what is this family of operator that generate transformation. That I really have no idea.
I'm at this point willing to forgo field theories and
Okay, we stop at least the live. I think it's 5:20.
Yeah. Hello?
I don't know if there is anybody still following also on. That one viewer might be Tobias that is checking.
Yeah, probably my computer is still. I just close it.
you are still following.
No, but you were following.
Everybody's now
Not the live, were you following the live stream?
officially.
Okay, so we'll stop the live stream now if is anybody
Okay.
watching.
Hello, Alessio.
Bye.
Wow.